Hello, and welcome to a new video series. In this video, I'll be writing, explaining, and then finally coding through Colaboratory or Python, the friction factor, and then two different events. Calculating the flow if we're given the head drop, and then continuously calculating the head drop if we're given the flow. So ahead here, I've given us writing down two equations. First of all, Bernoulli's equation in head form with respect to gravity. As you can see, all I did is just divide everything by gravity respectfully. And in this situation, today I'll be first starting with the first situation if we want to calculate the head drop if we're given flow. So starting from there, from Bernoulli's equation, we know that our diameter is going to be, or our pipe's not going to be changing, so we know that this velocity is going to remain constant, right? So we're not going to have this big difference. We can forget about this factor. And actually, if you can see under here, I have sorry about that. Under here, I have value, and if you remember, this is what we calculated from a previous video. This is the heating friction, heating friction. And we remember we were thinking about laminar flow and calculating the friction factor. This is what we were given, right? And if we want to write this in comparison to here, we divide this by gravity as well, so we would write this on the right hand side as well. We'll be using this to calculate our equation, or to use that in our code later on. And so if we look at this right now, we know what delta x is going to be is the length of the segment, diameter as well. Gravity is going to be constant as well. So what we don't know for here on the right hand side of this equation is the friction factor, and velocity. So for velocity, what we can do is something very simple. We know that the flow rate, right, is simply equal to the velocity times the area, right? So then we can rewrite this for the area in terms of the diameter, so that flow rate is equal to the velocity, and then simply area is we're doing pi r squared, so instead of the radius, we're going to have diameter over 2, so we're going to have d squared divided by 4, 2 squared, 4. And then we can go ahead and rewrite this in terms for velocity, so we get v simply equal to the flow rate times, or 4 times the flow rate times pi over the diameter squared, right? We can use this for our code, and then so all we're missing here for the right hand side of the equation is the fanning friction factor, and what I'm going to be doing to explain that is a little bit more complicated and be using a couple of different systems. So let's go ahead and jump into that. So here I have a Moody diagram, and pretty much what it represents is a whole bunch of different people have come together and derive different expressions to correlate Reynolds number, which we have here on the bottom, with the fanning friction factor with respect to the relative roughness of the pipe. And this covers both laminar and turbulent flow. As you can see, this is where it switches off in transition zone and turns into turbulent regime, and we have all these different expressions for the Reynolds number, fanning friction factor, and the roughness. And if you can notice anything, you can see for laminar flow that we have it is equal to 64 over Reynolds number. And if you recall from our previous video in our second series, we solved that in the laminar flow, the fanning friction factor is simply equal to 16 over Reynolds number. And this is because this is based on the Darcy friction factor, which is 4 times larger than the Moody's. So what I have over here is Darcy's friction factor, which is talking about which is what they use to express this Moody diagram. And what it is just a whole bunch of different expressions, like as I explained. It is a whole bunch of different approximations to derive, that was used to derive this diagram. And for this video's purposes, we will be using Churchill's equation, which is this right here. And as you can recall, it reads up here, it says the only equation that can be evaluated for very slow flow for when the Reynolds number is less than 1. So we're going to be using the Churchill equation to use this fanning friction factor. And then, however, as I said before, here the laminar flows is said to be 64 over Reynolds number. However, we came to find that it is 16 over Reynolds number, so we know that this Darcy friction factor is 4 times larger, so that we don't have to multiply this right-hand side by 8, but rather by 2. So we can go ahead and get started and write Churchill's equation, plug these two in for our equation, and then go from there to solve for our drophead equation. So I'm going ahead and input 2 things, numpy, so we know we're always going to be using that, and then I'm going to be using the root function, and we'll be explaining that later on. That is for the second part of this video. So for now, I'm just going to stick with the first part we're deriving for the drophead side. So like I said, we're going to go plug in Churchill's equation. So I'm going to define Churchill, and what we're going to be putting is Reynolds number, right, and the relative roughness, right. And then we're going to be plugging in these 2 equations, theta 1, theta 2, and then be returning our value, right? So I'm going to go ahead and plug that in. Theta 1. I think theta 1 should be good. I think theta 1 and theta 2 should be good. I'm just going to do friction factor, right? Should be good. Make this just to make sure. Then we're going to want to return this times 2, so theta 1 and theta 2 come in. An extra square here, 1.5. And 1/12. this is that. So I have this plus this. Alright, we're just going to run it through, and then what we can do is just test this function, make sure that gives some values, make sure that something works. So we can do Reynolds number, we can do it 16 over Reynolds number, so do 16 over 1600, do 1600 and give it roughness the same, 0.01, and what we should get is 16 over 1600, which is 0.01, which is right. Now what we can do for a little bit of turbulent flow, a little bit of a higher number, we can do 10 to the 6, go up here, an easy number, 0.01. If we look at it, seems to be just under 0.04, right? Match it up, so it should be like 0.038. So we put in, let's see, we said we're doing 1e to the 6, right? And a roughness of 0.01, right? And then we said we're getting a friction factor of 0.038. So if we do 0.038 divided by 4, we should get roughly 0.0095. If we run this through, that is roughly what we get, right? So we know that this Churchill equation is, we plugged it in right from this. So we can go ahead and then use this Churchill equation to then plug in for our drop head, right? So let's go ahead and create a new function, fine, and we're going to call it HD for head drop, nice and simple. What we're going to have in here, we're going to have 4 different variables, right? We're going to have flow rate, right? We're going to have the length of the pipe, and then we're going to have the diameter, and then the roughness, right? And then, obviously, if you remember, this is what we want to plug out, right? The right-hand side, which is this. It's going to be 2f delta x dv squared. So we need all of these values. So let's go ahead and plug them in. Start off with v. Actually, I'm going to put this side to side and make it a little bit easier to work. Set that the velocity is going to be equal to, I'm going to go ahead and plug these in. Okay. I'm just going to go ahead and say turn this already so we know what we want. We're going to have 2 f squared. And the F, any friction factor, is Churchill equation, right? Then we're going to have to plug in Reynolds number as well, right? Which remember, right, rho dv, I don't know what I had grade for it, apologize. Rho divided by dv divided by mu. Okay. And if you recall, there's some unknown that we have. Go ahead and put these in here for later. Alright. unknowns, we need rho, we need mu, and we need gravity, right? Okay, make sure it's all good. Yeah, I thought this was wrong. Okay. This should be, I don't know why this derivation is messed up, sorry. So we should have V is equal to 4Q over pi d squared. Apologize for that. Okay. Over P pi times d squared. Alright, I think it should be good now. Rho and mu, we know that we're just going to be used for the density of water for an example, and we know that's 1e to the third. Then mu, we know it's negative third. And then gravity, we're just going to be using 9.81. These through, and I think this should be good too as well. So what we can do is just test this out, give it some values to make sure that it's good, and it should push it out in meters, right? So what we can do is we can say with flow rate 0.1, altitude of 10 meters, or length of 10 meters, density is also 0.1, then a surface roughness of 5 to the negative thirds. If you run that through, we get a value of 25.2 meters for the head drop, and this could be a simply just a change in the pressure, a change in altitude, or even a combination of the two. So now, since we've gone ahead and calculated the head drop if we're given the flow, or the head drop if we're given the flow, now we want to do the opposite and calculate the flow if we have the head drop. So before we get too deep into calculating the flow, depending on the head drop, before I want to talk about our root function, and we're going to be using the root function for the solution for our flow rate. And how we're going to do this, we've used previous videos, we've been using that many times, but pretty much we're going to be using a function within a function. Before we do that, there's one missing step. We need to do one more derivation. So let's go onto the whiteboard and do that. So what we're going to be using is kind of this concept here. However, we're going to be finding the head drop, right? And for this situation, I'm going to call the head drop beta. So I'm going to call beta, and that's going to be equal to the left-hand side of this equation, right, of Bernoulli's equation. And one thing we have to think about is that the fanning friction factor and everything is going to be in terms of negative, right? However, when we have a positive head drop, we're going to have to return it in values that are not going to mess up the Python code, so we're going to want it to be positive. So this is simply going to be a big F over gravity. So then that we get that beta, which is going to be the head drop, is going to be equal to, what do we have, 2 times the fanning friction factor times dx, but now since we're using L, I'm going to use L for now, times v squared over dg, right? Then what we can do is solve for v, right? So that we get that the velocity situation multiplied by dg, so that we get beta times dg divided by this whole fraction, so 2FL, 2 times the fanning friction factor times the length of the pipe. This is all going to be square rooted, right, because we have v squared. That's the value for velocity, and then if we want to get the flow rate, I'm just going to make this Q. So if you want the flow rate, and this we're going to be using for our code, we want to simply multiply it by the cross-sectional area, right? So pi r squared, simply multiply it by pi d squared over 4, right? Because r is the diameter over 2, right? Simple. Okay, and we're going to be using this expression for our new Python code, and again we're using the root solver to calculate our flow. So again, for our expression for the flow, we're going to have another equation. Like I said, for root, we're going to have an equation within an equation. So we're going to define, we're finding the flow. I'm just going to, why not call it flow? Then again, we're going to have 4 different variables going through this, right? We're going to have the same. We're going to have the head drop, length, diameter, and then the roughness, right? All the same except for the flow, it's going to be the head drop. And then again, we're going to have another equation, and then we're going to call it a simple equation. And then we're going to be unpacking it, right, for the flow. So I'm just going to call it x, and unpack it, right? Right? And then what we're going to want to return out of here is the head drop, right? We want to see the difference between these two values, right? So we want to minimize these two values, right? Sorry, actually, I just remembered this could be beta, as that's what we solved for earlier, our Q. Unpack this. So what we want to return, as I said, is the difference. So we want to return beta, right? Minus what we get here from our head drop. Q, L, D, E, right? And that's for our root function. Then we can go ahead, then we're going to want to return our Q value. And then, as you recall, we solved for our Q, and that's what we're going to be using for beta. And I'm going to call this Q guess, because we're guessing to make sure, as we're saying the root function, we want to minimize it, right? So we're going to use this, right? So let's go ahead and put that in. Square root, square root, right? Then we want to multiply, so we want double beta times gravity, and all of that divided by 2 times length times, and then for the Fanning friction factor, I'm going to call it F guess, right? Good. And I'm going to put a guess here for the Fanning friction factor, and I think 0.01 is a fair value because it's roughly in the middle of this major of these values and situations. To plug this through, so let me make sure everything's okay. Clean this up here. Right, and then we can return our value. We said we wanted our root function, so return a root, and if we recall, what we want to plug in parameters, what do we have? We're going to be using we want to minimize this first value, right, of this equation, so we want return equation, right? with QGuess being right. QGuess. Pulling out the first value of this, right? Okay, should be good, I think, right? Let's this up. Should be good, right? Make sure again. Okay, so this looks pretty good. This looks what it should be. To make sure that this runs smoothly, what we can do is plug in our values from a previous head drop equation into here to see if they work. So we call flow. Then for beta, I'm going to be using these values from here. So I'm just going to copy and paste this exactly. And then for the length, we're going to still going to have 10. Then diameter is 0.1. And surface roughness, again, 5e thirds. And as I press Shift Enter, what should we get here? What we should get is 0.1, right? We want to get the flow of 2.1 meters per second squared. So let's see. That's roughly what we get, right? Pretty much rounded, just some small errors. I'm sure if we put this to 1.9, we'll get there, some small things like that. So there we have it. Here are the two different situations that we can be focusing on, either given our head drop and determining the flow rate, or determining the head drop through the flow rate. So there you have it. Hopefully this video will help you guys, and hope to see you next week. Thank you.